So what does self-attention do, right? Say this is that sequence, right? So the animal, this long sequence, because it's self-attention, of course, this is the same, right? So it's referring to itself. So if we want to encode, for example, it, right, in a sequence, and then the it should refer to all the words before and after. And here, well, the self-attention kind of learns correctly. It learns that it refers to street. Right, so here, basically here is the attention scores, or right. So it gives the distribution of the weight over these edges, and it gives more importance to the street. So here is shows the concrete examples of how you calculate the self-attention, right? So here, say we have thinking machines, and then first we have just extract a simple word embeddings from the thinking and machine. And then we have some transformation matrix, right? And then remember we need queries and values. And here they have the keys as well. I think the keys plays the part as the values. Earlier, we directly compare values and the queries. While here they add one more vector to compare it with the queries, right? So every time they just compare, for example, how similar keys are to the queries, and then use the similarity score to calculate the weighted sum of the values. So they have some additional kind of vectors to compute for similarity. And how they generate the queries, keys, and values, they use kind of a transformation matrix. For example, you have an embedding of dimension of 4, and then transformation matrix is 4 by 3. And then once you multiply them together, you get a vector of dimension of 3, right? And that becomes the queries. And again, that you also have a separate transformation matrix for keys and values. So this is how you get your queries, keys, and values. And then you can see here, again, I think in the original paper, they still use the dot product, one very straightforward way to calculate the similarity. And then, for example, you dot product Q1 and K1. This is the number you get. And then they do some normalization divided by the dimension. What's your dimensionality of the vector? And in the original paper, the dimensionality is 64. So all of these vectors the length of 64, and they divide it by 8. So the score divided by 8, and then they apply a softmax function to this vector, and that transforms this vector into a distribution. Right? And then we use this distribution values, multiply this with the regional values, or with the values, and then it gives you this, and then then we sum it up together, and that gives you a weighted sum. Right. So Z1 is a weighted sum of V1 and V2, and the weights comes from this softmax function. And we are doing this for all the word input, and that gives us Z1, Z2, etc. for until the end of the sequence. And so this is a step by step, and of course you can write this in a matrix form, right? So it's just Q and keys, so the queries, you compare queries and keys, and then you transform it into a distribution, of course, with some normalization of the dimensionality, and then you transform it into a distribution, and then you apply it to the matrix of values, and that gives you the kind of, I would love to call it contextual embeddings of the input. Because the Z is like considering all the other words in that sequence. So after self-attention, basically you transform your original embeddings into an embedding of new embeddings, I would say, that considers all the other words in the sequence. Okay, and then as I mentioned, there's a multi-hat. People usually use multi-hat. I think people use 8 or 16 attention. So what it means is, just as someone mentioned in that example, well, there can be other choices of where to focus. All right, so it's and then how to solve that, different possibilities, and then maybe then people event this like they call it multi-hat, basically just a different transformation matrix. Right? So in one possibility, you just apply this matrix, and then in a different attention hat, and you apply a different transformation matrix. Right? So this for hat 0, and this is for hat 1. And then you will get different matrix of queries, keys, and values. And of course, it will end up in different z's, right? So for multi-hats attention 0, you will get a matrix of z, and of course, different attention hat will gives you a different output of the transformation of x. And the next question is how we combine all of this together. Well, one simple way is just concatenate all of them together. Usually people use, for example, eight multi-hat. So you will see in the paper, people usually mention how many hats they use. Like, for example, if they use 8, so it means this, right? So 8 outputs, 8 different z's from that. And then they will concatenate all of these hats together. And of course, you want to control the size of the dimension. And one direct way to control it, of course, is to just apply another transformation matrix and map it to any dimension you want, right? So this is the final z that is transformed from this concatenated matrix. So all of these weights is learned by the model, right? So all of this transformation matrix is learned, and also this is W is learned, and that will gives you the final Z matrix that captures all the information from all different attention heads. And this is your output from your self-attention layer, and we then later on forward this to the fully connected neural network in the encoder, in the transformer. Yeah, so it also gives you some example of it, right? So for example, if you use 8 hats, and then this just shows you different hat, which part of the words are the words that the attention or that word is paying attention to. So different hat will gives you a different attention scores. For example, the orange one focus on the animal, maybe, and the green one is street and somehow tired also. Right? And it sometimes hard to explain to explain exactly what it's focusing on, but definitely is like some part of the sequence. And of course, if you are showing all the 8, it becomes even more difficult to understand what is focusing on. And to my understanding, I believe once you extract these attention outputs, and then the next is for the forward neural network to figure out which attention is more correct than the others, and maybe there's a better way to combine different attention outputs together to get even better attention for your final prediction task. Right? So that's why maybe the multi-hat is working better than just one choice.